Welcome to this tutorial on pseudo-Boolean solving and optimization, which is part of the bootcamp for the Satisfiability Theory, Practice and Beyond program at the Simons Institute for the Theory of Computing. I am Jakob Nordström from the University of Copenhagen and Lund University. So this pre-recorded part of the tutorial has 4 parts. Part 1 is on pseudo-Boolean preliminaries. And then in part 2, I'll talk about solving of decision problems. Then in part 3, about optimization problems when we're optimizing some objective function. And then there will be a 4th part about mixed integer linear programming. And the video will be divided into these 4 parts. And so this is the first part on pseudo-Boolean preliminaries. And I'll talk about what pseudo-Boolean functions and constraints are, what pseudo-Boolean solving and optimization means, give the formal definition, and then give some references for further reading. So what is a pseudo-Boolean function or a constraint? What does pseudo-Boolean mean apart from being a cool name? Well, it's simply what theoreticians would refer to as a function over the Boolean hypercube to the reals. So the inputs are Boolean variables, 0, 1 valued, and the output of a pseudo-Boolean function is a real number. And these pseudo-Boolean functions have been studied since the 1960s in operations research and in integer linear programming. We are interested in 2 restricted versions. First, where the functions f can be represented as polynomials. And in fact, throughout this tutorial, we'll be even more restrictive and consider functions that are representable as linear forms. And it turns out that this is a rich formalism for expressing different kinds of optimization problems. So many problems can be described as optimizing some linear objective function under linear pseudo-Boolean constraints. So why would we do pseudo-Boolean optimization when we have SAT? After all, the name of the program is the SAT program. But we also want to go beyond, and one reason to go beyond SAT to pseudo-Boolean is that it's a richer format than the conjunctive normal format used in SAT. For instance, if I want to write down that the sum of 6 Boolean variables is at least 3, then in a pseudo-Boolean format, I can just write down this inequality. Whereas if I write it as clauses, then I need this big chunk of clauses where we have, just to make sure we're on the same page regarding notation. So these are disjunctive clauses, x1 or x2 or x3 or x4 is the first clause, and then all the clauses are ANDed together. And it can be verified that a Boolean assignment satisfies all of these clauses simultaneously if and only if their sum is at least 3. Okay. So not only is the pseudo-Boolean format more expressive, but the kind of reasoning that we can use, pseudo-Boolean reasoning turns out to be exponentially stronger than the resolution-based reasoning that underlies conflict-driven clause learning, which is the dominant paradigm in SAT solving. And yet, the pseudo-Boolean format is close enough to SAT so that we can benefit from all the developments that have happened in SAT solving since the turn of the millennium. And since pseudo-Boolean problems are just another name, in fact, for 0-1 integer linear programs, as we will see, this means that we can also use ideas from 0-1 integer linear programming and try to exploit synergies. And in fact, a lot of what this tutorial is about is how to combine ideas from SAT, from 0-1 integer linear programming, and maybe other areas to construct good solvers. So what is a pseudo-Boolean constraint? Well, throughout this tutorial, a pseudo-Boolean constraint is going to be a 0-1 integer linear constraint. So it's a linear sum of literals, that is variables or negated variables, where the semantics is that x plus x bar, so the negation of x, is equal to 1. And the a's are all integers, and then the bow tie is some kind of comparator, so greater than, equal, less than equal, or equality, or strict inequality. And variables, as we said, take Boolean values. We think of 0 as false and 1 as true. In fact, we're going to, without loss of generality, use normalized form, where constraints are always written as greater than or equal constraints, and all coefficients are non-negative integers. And also the constant term on the right-hand side is a non-negative integer. And when a constraint is written in normalized form, this constant term is referred to as the degree of falsity, or just the degree of the constraint. So the clauses that we have in a conjunctive normal form, CNF formula, are just pseudo-Boolean constraints. We sum up the literals in the clause and require that at least one of them should be true. We just saw a cardinality constraint. That's another special type of pseudo-Boolean constraints that generalizes clauses. And then, of course, you can have general pseudo-Boolean constraints like x1 plus x2 bar plus 3x plus 4x4 bar plus 5x5 greater or equal 7, say. Okay. And in fact, it's not hard to see that this conversion to normalized form is without loss of generality. For instance, if we have this constraint, suppose we have the constraint minus x1 plus 2x2 minus 3x3 plus 4x4 minus 5x5, and we want this to be strictly negative, then in order to turn this into normalized form, we can first make the inequality non-strict. Strictly smaller than 0 just means less equal minus 1. And then to turn it into greater than or equal, we multiply by minus 1. And in the next step, we want to make all the coefficients positive. And we do this by replacing a negative literal minus L by minus 1 minus L bar. So if we do this, we get then x minus 2 times 1 minus x2 bar plus 3x minus 4 times 1 minus x4 bar plus 5x5 greater or equal 1. And now we collect all the constant term and shift them to the right-hand side. We get, in fact, the pseudo-Boolean constraint we had before, x1 plus 2x2 bar plus 3x3 plus 4x4 bar plus 5x5 greater or equal 7. And it should not be too hard to see that this will work in general. Also, if we have an equality, we just replace that by two inequalities, a greater than equality, a greater than equal, and a less than equal equality, and then we do this transformation for both of these constraints. So in view of this, we will always think of constraints as being in normalized form, but we can also freely allow ourselves to use syntactic sugar when convenient. So if we have a linear form AI Li where the sums of the coefficients is m, then a strict greater than inequality is just greater than or equal with the a plus 1 instead of a, and a less than equal equality sum AI Li less equal a, we just flip it around and get sum AI Li bar greater equal the total sum m of the coefficients minus a, and then similarly for strictly less than, and as we already said, for equality we replace it by two linear inequalities. So in the rest of this tutorial, whenever it is convenient, we will write the linear inequalities in whatever form is convenient for us, but whenever it matters, we implicitly assume that all constraints we're operating on are normalized. Another aspect that is worth commenting on is that we restricted our attention to linear constraints. But if we have non-linear constraints, say we have a polynomial sum of ai mi for I goes from 1 to k greater or equal a, where the mi's are monomials, then we can in fact write this as a collection of linear constraints we can linearize. We can introduce fresh variables yi for each monomial mi and write the linear sum ai yi greater or equal a, and then we specify for each yi that yi is 1 if and only if all literals in the monomial are 1. So this is possible, but we won't talk more about this during this tutorial. We'll, for the rest of this talk, we'll only consider linear constraints. Some convenient notation that we will use should be fairly obvious, but just to make clear what it means, if we have two constraints, then we can take their sum. If we have a constraint on a linear form, then I can just add this linear form to the constraint. Given a positive integer, I can multiply a linear constraint by that positive integer. And so we'll use this notation. And again, assuming that these resulting constraints are normalized whenever this matters. Some further notation that can sometimes be convenient, and I mentioned this also just to make sure that we are familiar with how constraints work and how we can play with them. If I have a pseudo-Boolean constraint C, some ai li greater or equal capital A, where I use this dot equality throughout the talk to denote syntactic equality, and the sum of the coefficients again is big M, then the negation of this constraint is also a pseudo-Boolean constraint. In fact, it's the same thing as the normalized form of sum of ai li strictly less than A. I can also have so-called reified constraints where I have a new variable z, and I can write down constraints saying, for instance, that if z is true, then the constraint c holds. And this would, if you think about it, this would be the constraint capital A times not z plus sum ai li greater or equal A, where A is the degree of falsity. So, and in the other direction, I can say that the constraint implies that z is true for a fresh variable z by writing down the constraint m minus a plus 1 times z plus sum of ai li bar greater or equal m minus a plus 1. And if you just take a minute offline, you verify that indeed these constraints mean what the notation suggests that they should mean. And in fact, you can do the calculations that if I take any constraint C and not C and I add them up, then I get contradiction, which is saying what we know, namely that both constraints cannot really be true simultaneously. So contradiction is 0 greater or equal 1. The reification constraint saying that the constraint C implies Z is in fact the same thing as saying that not Z implies not C, which is also easy to verify and it seems natural. And the way we can play with reified constraints is that if I have derived now that Z is true, so Z greater or equal 1, and I multiply it with the degree of the constraint C, and then add this to the constraint Z implies C, then indeed I get C back. And in a similar way, if I take the constraint saying that C implies Z and I add the constraint C to it, then I get that Z is true. In fact, I get that Z times the degree of falsity of the negated constraint is 1, but clearly that implies that Z is 1. Okay, so I'm saying this just to play around with the constraints to make sure that we're on the same page. So a pseudo-Boolean formula now is simply a conjunction of pseudo-Boolean constraints. And so sometimes we can write this as the set of constraints. Here I write it down as a conjunction of the constraints to make explicit that we, in order for the pseudo-Boolean formula to be satisfied, all constraints should be satisfied And pseudo-Boolean solving is the problem given a pseudo-Boolean formula to decide whether it is satisfiable or whether it is feasible, is another term that is used for this. A pseudo-Boolean optimization problem is where we have, in addition to a pseudo-Boolean formula f, also an objective function, which I'll tend to write sum of I, summing over I, wi, li, and we want to minimize this objective function. So whenever we have a pseudo-Boolean optimization problem in this talk, we always want to minimize the objective. And this is, of course, without loss of generality, because if we want to maximize, we can just negate the objective function and then minimize that instead. I said that pseudo-Boolean optimization allows us to express many problems in a natural and concise way. And just to give some examples of this, if G is an undirected graph and we have a weight function on the vertices V, then weighted minimum vertex cover is simply asking for a vertex cover. So we have a variable for every vertex. These are the vertices we're choosing to be included in the cover. So a vertex is in the cover if xv is 1. And for every edge, we want one of the endpoints in the cover, but then we want to minimize the cost of the cover. So summing over the cover, summing up the weights of all these vertices. Another problem that is similarly easy to express is weighted maximum clique. So in a clique, we want to pick as many vertices v as we can, with the restriction that if uv is not an edge, then we cannot pick both u and v. So under this restriction, we want to maximize the sum of the chosen vertices, or since we're insisting on minimization, we just add a negation in front. Finally, another problem slightly more general that will be relevant later in this tutorial is weighted minimum hitting set. So here we have a collection of sets living in some universe, and we have again a weight function on all the elements in the universe, and we want to find a hitting set. So a hitting set is just a set that has a non-empty intersection with all the sets in our collection. And for such a hitting set, we're looking at one of minimal weight. So summing up all the weights of the chosen elements in the set, the weight should be minimal. It's not hard to see that this is just a generalization of vertex cover. And the pseudo-Boolean optimization formalization of this is, again, just we're minimizing the linear sum of all the variables, one variable per element, times its weight, under the restriction that for every set, at least one element in it should be chosen. And it's worth noting that, in fact, all of these examples that I gave are even more restricted than general pseudo-Boolean optimization problems. In fact, here we're asked to optimize a linear function subject to just the CNF formula, because all the constraints we see are just clauses. So already this is quite an expressive framework, although in general, of course, it might be that the constraints should also be general pseudo-Boolean constraints. So what we will talk about in the rest of this tutorial is, first, we're going to talk about pseudo-Boolean solving and optimization. Basically, what I mean by this is that we're going to start with SAT solving, and inspired by SAT solving, we're going to take these conflict-driven techniques and try to lift them to the pseudo-Boolean setting. And this is what most of the tutorial will be about. Then we'll also talk about the very closely related topic of max SAT solving. And then in the final part of the tutorial, we'll talk about integer linear programming, or more generally, mixed integer linear programming, or MIP. And very roughly, one can say that an interesting difference between these approaches is that for SAT solving and pseudo-Boolean solving, you are always doing Boolean reasoning, and you're focusing on finding integral solutions, so 0-1 solutions, and trying to zoom in on the optimal one. In some sense, integer linear programming or mixed integer linear programming tends to operate from the other direction. You relax the problem and find optimal non-integral solutions. And then from there, you try to search for good integer solutions nearby, as it were. But for all of these settings, a basic trade-off that we will see several times during this talk is the trade-off between inference power versus inference speed, where some solvers will optimize being very, very smart, though this takes more time, and other solvers sacrifice intelligence maybe for speed and hoping that raw speed will compensate for being slightly dumber with your inference. Although this will be a somewhat long collection of videos, it will still be only a very, very selective survey of this area. So some references for further reading. Well, 4 chapters in the Handbook of Satisfiability that is just out. The 2nd edition is being printed and distributed as we speak. And it's a fantastic book. In particular, I can recommend chapter 7 on proof complexity and SAT solving, which contains a lot of the material I'm going to talk about. Also chapters 23 and 24 on max SAT. And chapter 8 also contains material on pseudo-Boolean solving. For mixed integer linear programming, there is nothing in the Handbook of SAT. But a good starting point might be these papers that I'm linking to here. And then for MaxSat and mixed integer linear programming, I can also recommend the tutorials, the MaxSat tutorial at ECAI 20 last year. And for MIP, there's a very nice tutorial by Ambros Gleixner at a workshop in Oaxaca a couple of years back. And those will give more details on MaxSat and MIP, which are topics that are not so well covered in this tutorial. So with this, I conclude the first part of the tutorial on pseudo-Boolean solving and optimization, where we just surveyed the preliminaries. Next up, we're going to talk about how to solve pseudo-Boolean decision problem, how to determine whether pseudo-Boolean formulas are satisfiable or feasible. And then later on, we'll talk about different ways of optimizing.